It is indeed possible to install a 208 volts primary to 24 volt secondary 400 Hz control transformer on a 60 Hz system. However, there are crucial considerations to keep in mind for safe and efficient operation. Firstly, voltage compatibility is paramount. The transformer's primary voltage rating, which is 208 volts in this case, must align with the voltage of the 60 Hz system. If the system voltage deviates significantly, either being higher or lower than 208 volts, the transformer may not function as intended and could potentially sustain damage. It's imperative to verify that the primary voltage matches the system voltage to prevent any adverse effects. Secondly, the frequency difference between the transformer's design frequency of 400 Hz and the system frequency of 60 Hz will influence its performance. Although the transformer will operate on a 60 Hz system, the output voltage will be lower compared to its performance on a 400 Hz system. Furthermore, the transformer may experience increased core losses when operating at 60 Hz, leading to higher operating temperatures. This is an important factor to consider when determining the transformer's suitability for the application. Thirdly, the transformer rating, expressed in volt amps or VA, must be adequate to accommodate the load connected to the secondary side. If the load exceeds the transformer's VA rating, it may overheat and eventually fail. Therefore, it's crucial to calculate the total volt amp requirement of the connected load and select a transformer with a sufficient VA rating to handle it safely. It is always better to oversize slightly if one has any doubt in the loads. Fourthly, proper grounding is essential for ensuring electrical safety. The transformer must be grounded in accordance with local electrical codes and regulations. Grounding provides a path for fault currents to flow back to the source, tripping circuit breakers or fuses and preventing electrical shock hazards. Refer to the National Electrical Code, specifically Article 250, for detailed grounding requirements. Fifthly, adequate cooling is necessary to prevent the transformer from overheating. The transformer should be installed in a well-ventilated area to facilitate heat dissipation. If the transformer is enclosed, it may be necessary to install a fan or other cooling device to maintain a safe operating temperature. Overheating can significantly reduce the transformer's lifespan and potentially lead to failure. In addition to these core considerations, it's also important to be aware of other potential issues. For example, the transformer's inrush current may be higher when energized on a 60 Hz system compared to a 400 Hz system. This is because the core may saturate more easily at the lower frequency. An inrush current limiting device may be needed to mitigate this issue. Also, it is imperative to ensure the transformer has proper overcurrent protection. Fuses or circuit breakers should be installed on both the primary and secondary sides of the transformer to protect against overloads and short circuits. The size of the overcurrent protection devices should be carefully selected based on the transformer's VA rating and the applicable electrical codes. Considering these factors will ensure the safe and proper use of a 400 Hz transformer on a 60 Hz electrical system. It is also important to consult with a qualified electrician or electrical engineer to ensure that the installation complies with all applicable codes and regulations. Neglecting any of these factors could lead to electrical hazards, equipment damage, or system malfunction. Understanding core losses is also very important. Core losses, also known as ion losses, are energy losses in a transformer core due to the alternating magnetic flux. These losses are primarily caused by two phenomena, hysteresis and eddy currents. Hysteresis losses are caused by the energy required to repeatedly magnetize and demagnetize the core material as the alternating magnetic field changes direction. The amount of hysteresis loss depends on the properties of the core material and the frequency of the alternating magnetic field. Eddy current losses are caused by circulating currents induced in the core material by the changing magnetic field. These currents flow in closed loops within the core and dissipate energy in the form of heat. The amount of eddy current loss depends on the resistivity of the core material, the frequency of the alternating magnetic field, and the thickness of the core laminations. Because the frequency is much lower at 60 Hz, it is reasonable to assume that the core losses will increase, even though the applied voltage is designed for 208 volts, which the transformer will reduce down to 24 volts, so you may not have to worry about voltage saturation and the core creating extra heat to worry about. Because the frequency is lower, the transformer may saturate the core, which results in heat. Saturation occurs when the magnetic flux density in the core reaches its maximum value. When the core is saturated, further increases in current do not result in a proportional increase in magnetic flux. This can lead to distortion of the output voltage waveform and increased losses. Also, one needs to understand the difference between voltage and volt-amps. Voltage is the electrical potential difference between 2 points measured in volts. It represents the force that drives electric current through a circuit. Volt-amps, on the other hand, are a measure of apparent power in an alternating current circuit. It is the product of voltage and current without taking into account the phase angle between them. The volt-amp rating of a transformer indicates its capacity to deliver power to a load. It is important to select a transformer with a VA rating that is sufficient to handle the load requirements. The power factor is the ratio of real power measured in watts to apparent power measured in volt-amps. It represents the efficiency with which electrical power is used. A power factor of 1 indicates that all of the apparent power is being used as real power, while a power factor less than 1 indicates that some of the apparent power is being wasted. Inductive loads, such as motors and transformers, typically have a power factor less than 1. It is also prudent to measure the temperature rise in the transformer. The temperature rise is the difference between the transformer's operating temperature and the ambient temperature. Transformers are designed to operate within a certain temperature range. Exceeding the maximum temperature rating can damage the transformer and shorten its lifespan. The temperature rise should be measured under normal operating conditions using a thermometer or infrared camera. The temperature rise should be within the limits specified by the manufacturer. Also, you should also consider harmonic distortion. Harmonic distortion is the presence of harmonic frequencies in an alternating current waveform. Harmonics are integer multiples of the fundamental frequency. For example, if the fundamental frequency is 60 Hz, the second harmonic is 120 Hz, the third harmonic is 180 Hz, and so on. Harmonic distortion can be caused by nonlinear loads such as electronic devices and switching power supplies. Harmonic distortion can cause a number of problems, including overheating of transformers, increased losses, and interference with other equipment. If harmonic distortion is a concern, it may be necessary to install harmonic filters to reduce the harmonic content of a waveform. Finally, it is necessary to perform routine maintenance. Routine maintenance is essential for ensuring the long-term reliability of the transformer. Maintenance tasks may include visual inspection, cleaning, and testing. Visual inspection should be performed regularly to check for signs of damage, such as cracks, leaks, or corrosion. The transformer should be cleaned periodically to remove dust and debris, which can reduce cooling efficiency. Testing should be performed to verify that the transformer is operating within its specifications. Testing may include measuring the voltage, current, and temperature of the transformer. By following these guidelines, you can ensure the safe and reliable operation of a 400 Hz transformer on a 60 Hz system. Always prioritize safety and consult with qualified professionals when necessary. Moreover, one should keep in mind that the impedance of the transformer is also key. Transformer impedance is the opposition to the flow of alternating current in the transformer windings. It is expressed as a percentage of the transformer's volt-amp rating. Transformer impedance is important for several reasons. Firstly, it limits the fault current that flows during a short circuit. A higher impedance transformer will have a lower fault current, which can help to protect equipment from damage. Secondly, it affects the voltage regulation of the transformer. Voltage regulation is the change in secondary voltage from no load to full load conditions. A lower impedance transformer will have better voltage regulation. Thirdly, it affects the parallel operation of transformers. When connecting transformers in parallel, It is important to ensure that they have similar impedances. Transformers with significantly different impedances may not share the load equally. The impedance of the transformer is determined by the design of the windings and the core. It is typically specified on the transformer nameplate. When selecting a transformer, it is important to consider the impedance requirements of the application. Furthermore, one needs to think about the type of transformer. The type of transformer, such as dry type or liquid filled, also affects its performance and suitability for different applications. Dry type transformers are cooled by air and are typically used indoors. Liquid filled transformers are cooled by oil or other dielectric fluid and are typically used outdoors. Dry type transformers are generally less expensive and easier to maintain than liquid filled transformers. However, liquid-filled transformers have a higher overload capacity and are more resistant to moisture and contamination. The choice between dry-type and liquid-filled transformers depends on the specific requirements of the application. Also, one needs to understand the core material. The core material of the transformer affects its efficiency and performance. The most common core materials are silicon steel and amorphous steel. Silicon steel is a ferromagnetic material that is widely used in transformer cores. It has a high permeability and low hysteresis loss. Amorphous steel is a relatively new material that has even lower losses than silicon steel. However, amorphous steel is more expensive and more difficult to manufacture. The choice of core material depends on the desired efficiency and performance of the transformer. One more key thing is the insulation. The insulation of the transformer windings is critical for preventing short circuits. The insulation must be able to withstand the voltage stresses that occur during normal operation and during fault conditions. The insulation is typically made of paper, varnish, or epoxy resin. The insulation thickness and type depend on the voltage rating of the transformer. Also, you need to ensure you have considered the proper taps. Some transformers have taps on the primary or secondary windings that allow the voltage ratio to be adjusted. Taps are useful for compensating for voltage variations in the supply voltage. They can also be used to adjust the output voltage to match the load requirement. The tap settings should be selected carefully to ensure that the transformer operates within its voltage rating. Also, make sure the transformer is properly ventilated. Transformers generate heat during operation. Adequate ventilation is essential for dissipating this heat and preventing the transformer from overheating. The ventilation requirements depend on the size and type of transformer. Dry-type transformers typically require more ventilation than liquid-filled transformers. The ventilation opening should be kept clear of obstructions to ensure proper airflow. Furthermore, you need to think about the altitude. The altitude at which the transformer is installed affects its cooling performance. At higher altitudes, the air is less dense, which reduces the cooling efficiency. Transformers that are installed at high altitudes may need to be deaerated to prevent overheating. Deaerating involves reducing the transformer's volt-amp rating to compensate for the reduced cooling efficiency. Also, remember about the ambient temperature. The ambient temperature also affects the transformer's cooling performance. Transformers are designed to operate within a certain ambient temperature range. Exceeding the maximum ambient temperature can cause the transformer to overheat. If the ambient temperature is high, it may be necessary to provide additional cooling, such as forced air cooling or liquid cooling. And never forget to do a proper site survey. Before installing a transformer, it is important to conduct a site survey to assess the installation conditions. The site survey should include the following considerations. Firstly, the available space. Secondly, the ambient temperature. Thirdly, the altitude. Fourthly, the ventilation. Fifthly, the accessibility. Sixthly, the proximity to other equipment. And seventhly, the presence of any hazards, such as flammable materials or corrosive chemicals. The site survey will help to ensure that the transformer is installed in a safe and suitable location. Keep in mind the regulations because the installation of transformers is subject to various regulations and standards. These regulations are designed to ensure the safety and reliability of electrical systems. The regulations may vary depending on the location and the type of installation. It is important to consult with a qualified electrician or electrical engineer to ensure that the installation complies with all applicable regulations. After everything is done, it is a great idea to do a commissioning test. After the transformer is installed, it is important to perform commissioning tests to verify that it is operating correctly. Commissioning tests may include measuring the voltage, current, impedance, and temperature of the transformer. The test results should be compared to the manufacturer's specifications to ensure that the transformer is operating within its design limits. And lastly, proper documentation. It is important to maintain accurate documentation of the transformer installation, including the transformer specifications, the installation procedures, the test results, and the maintenance records. This documentation will be helpful for troubleshooting and maintenance purposes. Always ensure that you follow these steps and that all the aspects have been accounted for.